Hi, this is Dr. Vev. We will now discuss vector triple product of three vectors. As you can see from the structure of the Cartesian domain space, you take each vector from the space of R3 parenthesis R, which means it's a three-dimensional vector with coefficients drawn from real numbers, and you somehow do something to them to produce another vector. Well, the thing that you do to them is fairly obvious. If you take the cross product of two vectors, and last time we took the cross product of two vectors and then took a further dot product with a third vector to get a scalar, all we now have to do is take a cross product with a third vector instead. Can this be generalized to n vectors? Absolutely. You can keep taking cross products again and again and again. So we'll stop at 3 though, because it gets pretty complicated and not very obvious what the interpretations are. So the triple vector product of A, B, and C is simply defined as A cross B cross C. But here we have to be very careful of the parenthesis placement. You cannot just place the parenthesis wherever you want, because A cross B cross C is not equal in either magnitude or direction to A cross B cross C. So we have to be very careful there. For example, B cross C is perpendicular to B and C, and A cross B cross C is perpendicular to both A and to B cross C, whereas A cross B is perpendicular to both A and B, and A cross B cross C is perpendicular to both of these things. So later on we'll see a better formula way of looking at the difference between these two. That formula is actually something that I want to get into right away. There are some properties of the triple vector product which you should read my notes to get. It's got the trilinear property that the triple scalar product has got. It's non-associative, which I just indicated here. And there's something called a Jacobi identity, which I won't get into, and that also you can find in my notes. But what I'm more interested in showing you is a certain identity here that we're going to prove now. And that identity is called Lagrange's identity. As you study higher mathematics, you'll realize that Lagrange is all over the place. People like Lagrange, Jacobi, Laplace, they're all over the place in higher mathematics, because these are the people that were the intellectual descendants of Isaac Newton and people after him, and they developed mathematics to a very high level. So the notion of triple vector product and similar notions were due to workers in the era of Lagrange, and Lagrange proved a ton of these identities in every possible subject. So if you have an identity and you don't know what to call it, it's a good chance that you should call it Lagrange identity. So this identity is the following: A cross B cross C is A dot C B minus A dot B times C. Now that's a pretty remarkable statement. It actually gives you a vector space decomposition of the vector triple product. It tells you, hey, it's just a linear combination of the vectors B and C. The interesting thing that this can be thought of as some coefficient alpha, and that can be thought of as a coefficient beta. So this is equal to alpha B. I'll think of the minus sign as included in the beta. So this is minus alpha B plus beta C. So somehow A cross B cross C is not in the plane of A, it's in the plane of B cross C. That makes sense, because if each time you take a cross product, you're getting lifted out of the plane. So if you take a cross product of B cross C, let me draw a picture. Here I have vector B, here I have vector C, and if you do a vector cross product of B cross C, remember the cross product is perpendicular to both the vector B and the vector C. So I'll put those two 90-degree angles to indicate that. That's your B cross C. And now if you cross it with another vector A, some vector I'll draw here, that result has to be perpendicular to both B cross C and to A. Well, if it's perpendicular to B cross C, you're already saying that it's in the plane of B and C, because any vector that's perpendicular to B cross C must be in the plane of B and C. So this vector, which is A cross B cross C, is already in the plane of B and C. It's been plunked back into that plane. And of course, it makes a 90-degree angle with each of these fellows. Let me try my best to make this 90-degree obvious. It's not easy. So it's 90 degrees with respect to both A and to B cross C. Okay, and that's back in the plane of B and C. So you see that something like this should be true. Now what these coefficients are, of course, can be got by many methods, and two of the methods I indicate on my notes involve a symmetry argument, or simply selecting certain components of B and C to be 0 and then working it out component wise. You can look at those alternative ways of getting Lagrange's identity. But the most rigorous way of getting Lagrange's identity is using what's called the double epsilon identity. And that's what I want to focus on in this video, because we'll be using this a lot in proving vector identities in future. So what does this tell us? Suppose we have two epsilon Levi-Civita tensors, and let's call it RMN and epsilon RPQ. Clearly, you see that the index R is being summed over, but not the indices M, N, P, or Q by Einstein summation convention. This actually is equal to, in one of the homework problems, you will have a chance to show this as an extra credit problem. And observe this amazing structure. Of course, the index R doesn't show up because it was summed here, but every other index shows up. Now, if you look at this carefully, you'll see some trends. And I wish I could give you a chance to examine it yourself. So if you want to pause the video, go ahead and do that. R is being summed over, so you're never going to see that. M and P occur here, so that's the indices in the right order, N and Q. So the first two deltas get indices in the right order, M, the second index of this epsilon and the second index of that epsilon, the third index of this epsilon and the third index of that epsilon. The minus sign comes with the remaining way of writing these indices. I can take the second index of this epsilon and the third index of that epsilon. So if I do this and this, this and this, that gives me the plus term. And then if I do this and this, and this and this, that gives me the minus term. So that's basically what's happening in this. Once you get a hang of it, and by working out a few problems, you'll have no trouble remembering the order. And in any case, you can always look at the notes to remember. So this equation can be used to figure out Lagrange's identity. Let's do that. Let's try to find the ith component of the triple scalar product, A cross B cross C, the ith component thereof. Now we're going to think of B cross C temporarily as another vector. We'll call it D. So I'll call it A cross D I. Well, that by the epsilon ijk mechanics is just epsilon ijk aj dk. Now D all by itself is B cross C, because that was what I said here. So dk is going to be B cross C, the kth component of that, and that's going to be epsilon k lm bl cm. Now you observe the care with which I have avoided j and k, because it's already appears. Whatever indices appears in the other epsilon, I will stray away from. There's plenty of alphabets to choose from in even the Latin alphabet, so we can stick with other kinds of the L and M that come after K is what I've chosen. Now once you have this, I can put it back there and I get A cross B cross C. Ith term is going to be epsilon ijk. Now the epsilon ijk's are just scalars, so I can bring both the epsilons to the front. Epsilon klm, and then I can just put everything in whatever order I please. Now I like to keep A, B, C, D, so I'll write it as A, J, B, L, C, M, D, K. All right, now this cannot still be used directly because the R index which gets summed over should appear in the front. Well, that's easy. What we have to do now is to use the cyclic properties of epsilon ijk. Now if you remember, epsilon ijk has the symmetry of the clock. So you can go from I to j, j to k, and k to I with no loss. So in other words, epsilon ijk is the same as epsilon jki, and that's the same as epsilon kij. It doesn't matter how I play this game, I always get the same answer. So what I can do here is I can make that shift. Epsilon kij is more suitable to what I need. So I'll write this as epsilon kij, epsilon klm, and now you notice already this has got the same structure as that because the k index comes in the front. And then aj, bl, cm, that is there is no D. I don't know why I have this D all of a sudden. K, L, M, that D, there's no D there. I'll just remove the D. It's an error on my part. Okay, so that's what I have. That I got confused because D already was B cross C, and so I just need, when I looked at that, I put that too. So I just needed to have replaced dk with all that, so that D goes away. I wrote D also. So anyway, this is what I have. Now I can go ahead and use the double epsilon identity with no problems. So I get, be careful, delta, this is going to be I and L, delta J and M, minus delta I and M, delta J and L. And then I have AJ, BL, CM. Now here, we have gotten to a very good point actually. We're almost done. But what to feed each delta? Now, remember that the index I should remain unfed because the index I we need. So we can certainly saturate the index L here. So I can bring BL over there and provide delta IL some food. Once you satisfy a delta, put a parenthesis around it. J and M are not indices that appear here. So both of them should be fed together. So that gives me delta JM AJCM. And I'll do the same thing with the other delta. I should only be fed once because you need an I. Delta IM should only be fed once. So that gives me delta IM CM times delta JL, and that has to be fed twice, AJ BL. Well, the delta IJ, the Kronecker delta from an earlier video, you know that delta IJ is equal to +1 if I equals J and 0 if I is not equal to J. It's an on-off switch. It's a diagonal matrix. So this tells us that for any non-zero contribution, you better have I equal to L. And so I'll get BI. Now, why did I choose to write it as BI and not BL? Because on the left side, I have an I index free. So you should make sure to have an I index there. Here, you don't care. J has to be equal to M. You can either make M equal to J or J equal to M. You don't care. I'll just do J. So I'll get AJ, CJ. And there, again, I'll get CI times, here, I've already done AJ, CJ there. So let me favor L here. So I'll get AL, BL. Now, that's just another way of writing the dot product. So this gives me BI times A dot C minus CI times A dot B. I'm done because I showed the ith component of A cross B cross C is equal to that. So if I write it as vectors, I'll write it as A cross B cross C without writing the ith component. Then it's going to be B, because I'm not writing the ith component, times A dot C minus C times A dot B. And of course, it's more customary to put the scalars in front of the vectors, and that's how you get Lagrange's identity.